I'm Cédric Constantineau from Polytechnic Montreal, from the province of Quebec, Canada. And today I'm going to present about my research project, which is on fatigue strength behavior of fort and nickel molybdenum welds containing artificial discontinuities. So, in the province of Quebec, Canada, our electricity are made mostly from the river. And so hydraulic turbines, such as this one, the Francis turbine runners, are exploited by our industrial partner, Hydro-Québec, and are essential for renewable energy generation. So this Francis turbines runner has multiple blades, and these blades are connected to the crowns and the bends of the turbines. And so they are connected, joined by welding joints, and these joints has welding discontinuities, and it affects the material fatigue resistance, such as lack of fusions and internal inclusions. So problem statement, limited knowledge by our industrial partner, Hydro-Québec, restrict 410 nickel molybdenum fatigue strength prediction to the Kitagawa-Takahashi diagram. So this is a typical flaw that is created right after gouging, and it is perceived as a lack of fusion. So it forms worm-like shapes and can be measured on several millimeters. And this kind of defect are predicted by the Kitagawa-Takahashi diagram. So basically, it is a prediction of fatigue strength as a function of defect size. And we use the LEFM, linear elastic fracture mechanic based approach to predict the fatigue resistance. So, should volumetric defects in 410 nickel molybdenum be classified as notches instead of crack-like discontinuities. Cracks are more critical in terms of fatigue due to the infinite stress concentration factor. And what will be the impact on turbine stability? Higher predicted fatigue resistance, and it optimizes the design. So, the general objective of this project is to apply the generalized Azori-Lazarin approach to predict the fatigue resistance of 410 nickel molybdenum containing large volumetric defects. Basically, this is a diagram which predicts the fatigue strength as a function of the discontinuity size, but for different singularity exponent. For a crack case example, the singularity exponent is 0.5. But when we consider notches, the singularity exponent is decreasing. So we needed to introduce artificial defects in a base metal to do the fatigue test of some specimen. And so for the simple operation, this is a plate of S41-500 illustration. So it's basically stainless steel. And so we build it along this longitudinal axis. Then weld beads of 410 nickel molybdenum are deposited at the bottom of the cavity, and the flux residues are deposited all along the longitudinal axis. So this is a real-time picture of the process. So as you can see, this is flux residues that are deposited all along the longitudinal axis, and then it is covered by weld beads. Then the cavity is filled up with multiple weld beads, and then the excess is grooved. Same steps are done once over. So cavity, multiple weld beads, and then finally the excess is grooved. From there, a post-weld heat treatment is done at 605 degrees Celsius for 8 hours, and 15 fatigue specimens are machined through the plate with a metallographic sample, which is extracted from it. So this is the metallographic sample transverse surface, and as you can see in the middle, this is the discontinuity, which is surrounded by the yellow circle, and it is surrounded by the distribution of columnar and fine grained microsite. Micro-honest measurements indicated that the filler method was not locally affected by the discontinuity. Now the fun part. Every fatigue specimen was characterized by CT scan. So on the top picture, you can see this is a rough mesh from the post-processing of Dragonfly software and the smoothed specimen that was done with SolidWorks 3D CAD software. This is a comparison analysis of the specimen transverse surface. So on the left side, this is an this is a surface using light microscopy, and this is the actual mesh on this picture. So the smears from the transverse surface was removed to avoid any useless stress concentration. This is one of the specimen, and we applied the appropriate boundary condition and nominal stress with the material properties of stainless steel, and the constitutive law is linear elastic. Tetrahedral elements were used, with tenoids were used, and the bulk model was meshed with 200 micron, and a final mesh around the vicinity of the discontinuity. So for the fatigue testing procedure now, a load ratio of 0.1 was applied with a targeted number of cycles of 2 million. Frequency of 108 was used because we used a vibrophore. So to calculate the fatigue strain, a step loading method was used. So basically, to calculate it, the two last steps of this method are used in this equation. So on the picture A, this is the actual test on the vibrophore for one of the specimens with the artificial discontinuity. And on the picture B, you can see that this is the fracture surface with the remaining flux all along the longitudinal axis, the weld direction. So now, our main goal of this project, fatigue strain on a generalized Adjorey-Lazarin diagram. To do so, this is a comparative analysis of the real specimen with the finite element analysis one. Two-way represent the discontinuity size at the location where the y direction stress was maximum. From there, we retrieved the stress. We did the stress distribution at this location, and we retrieved essential variables such as singularity exponent of 0.3 for this specimen, for example, geometry factor, and stress concentration factor. From there, we can build the Adjorey-Lazarin diagram. And so the red dot represents the fatigue strength from our experiment. The black line represent the prediction from the notch theory. And then I superimpose the LEFM, which seems to predict well the fatigue experiment. But this is one of the specimens. Now I'm going to show you for every specimen. So what I did a comparison between LEFM and the notch theory on this graph. This graph basically is on y-axis. This is the prediction of fatigue strain. The x-axis represents the experimental fatigue strain, and the dashed line, the black one, represent when the prediction equal the experiment. So basically the ideal prediction model. So the triangles that are mostly represented in red represent the notch theory, which is unsafe because it overestimates the experimental test. The prediction is overestimated. And so the LAFM represented by squares are mostly greens because it's a safe approach when using this graph, with a prediction accuracy of 84%. So basically, the LFM is a safe approach for this kind of volumetric defect that we can find in these welded joints. But why are LEFM prediction more accurate than the notch theory? So we did some fractographies here to see what's going on. So as you can see in picture B, for example, this is an ACM detail of the weld root, and you can see that there is a step-like feature, and so the height is different from the fracture surface. And we needed to do an interrupted test to identify more precisely the crack origin of this step-like feature, which emanates many ratchet marks finally. So this is the interrupted test. And you can see in black, this is the discontinuity, and a crack emanates from the weld root between weld beds at intersections. So a zoom-in picture shows us that there is two sharp corners, and one crack is emanating from a sharp corner. And another zoom-in picture shows us that this crack emanates from a small notch flux field feature. And this small notch has an approximately radius of 5 micron. And the CT scan contour shows us that it was undetected by the CT scan finally. Another reason why LEFM prediction is more accurate than the notch theory is cracks. Cracks occurring during welding operation. And you can see the variation with the EDS elemental mapping, which shows that the titanium, zirconium, which represent the flux residues, there is a good distribution between finally the flux residues, the cracks, and the fallow metal, and some flux residues were present in the cracks. So it may unbrittle the material. So summary of the work. The defects introduced in the weld behave like crack-like discontinuities, and 3 reasons explain why the LFM provides more accurate prediction than a notch theory. So first of all, small notches undetected by CT scan were produced at the superposition of weld beads. And these notches may have a singularity exponent closer to 0.5. Then cracks undetected by CT scan are prone to form during welding those cracks have a singularity exponent of 0.5. And like I mentioned on the last slide, foreign elements belonging to flux residues, such as zirconium, titanium, silicon, were found at the crack initiation site, and their presence can embrittle the material. So, industrial application of this research. Actual operational fatigue life of hydraulic turbines by our industrial partner, Hydro-Québec, is predicting using the LEFM-based approach. So non-destructive testing methods employed by manufacturers and operators of this welded assembly consider linear indication as crack and assessing weld defects through CT scan with a maximum resolution of 20 micron per voxel proves challenging, whereas conventional NDT methods employ lower resolution. So the main result of this research project is that volumetric defect, the safe recommendation for volumetric defect is to apply the Kitagawa-Takahashi diagram for predicting it. And so, as it provides a strength, fatigue strength precision of 84% when accounting for the maximum discontinuity size. So thank you, everyone. This is my references, and thank you.